Yeah, good evening to all. Good evening, students. So, am I visible and audible to all of you? Can you all able to see me? And just let me know in the chat box whether am I audible and visible to all of you. Yes? Yes. Thank you, Srish. Good. Yes. Thank you. Thank you. Yes. Thank you. Thank you so much, students. So, let's start today's class. So, yesterday I gave you some compounds, right? As a homework. Did you all do that? So yesterday we have discussed the nomenclature part, right? So nomenclature and the isomerism we have discussed yesterday. And did you all do the homework which I gave you? If you have done, it's good. Yes. Bunny Sunny. Good. Good. Okay, dear. Okay. Good. So if you try to do the homework or try to solve more number of questions every day, okay? Because exam is nearing, right? So try to solve more number of questions. And coordination compound is having a high weightage for your exam. So you should concentrate more on this lesson. So far we have completed the Werner's theory, nomenclature and isomerism part of this lesson. And today I am going to deal with the second theory of this lesson, which is the valence bond theory, VBT. Okay. So the topics that we are going to cover under valence bond theory are the introduction to valence bond theory and the valence bond theory for octahedral complexes and for tetrahedral complexes and for square planar complexes, and lastly the disadvantages, nothing but the limitations of valence bond theory. Okay. Now moving on to the introduction of valence bond theory. So basically it starts with the types of hybridization. Okay. So the main introduction or the valence bond theory is based on the hybridization of the orbitals. So we all know that hybridization is the intermixing of atomic orbitals, and we do have different types of hybridization like sp, sp2, sp3, sp3d, sp3d2, sp3d3. So all these are the types of hybridization. So this theory concentrates, or it is based on this hybridization. And this hybridization is decided on the basis of the magnetic moment. The measure of bond polarity is called as magnetic moment, right? Which is represented by the letter mu. So hybridization is based on the magnetic moment. And the magnetic moment can be calculated from the number of unpaired electrons present inside the system. Okay, in the D and F block elements also we have solved this type of question, right? So the same thing is here. So this theory focuses on this particular topic. So each hybridized orbital of a metal will interact with the ligand orbitals. Okay. So what this ligand will do, ligands are the electron donors, right? So they will give the electron pairs to the hybridized orbital of the metal. Metal orbital will be hybridized and the ligand will give its electron pair to the hybridized orbital of the metal. And because of this bond formation, a complex compound is formed. That's what we are calling as coordination complexes. Okay. Now, what are the types of hybridization that is going to be very important here in this coordination compounds lesson? Those are, we do have many types. The very important types are the tetrahedral. So the hybridization of a tetrahedral species is sp3. So for all the tetrahedral intermediate species, the coordination number will be 4, right? So this is the first hybridization, and the second hybridization is dsp2. Okay, the coordination number is again same, which is 4, but it is for square planar complexes. Okay, and the third type of hybridization is sp3d. sp3d geometry is trigonal bipyramidal, and the coordination number for trigonal bipyramidal, as you can see, it is 5. Okay, and lastly, sp3d2. The geometry of sp3d2 hybridization is octahedral, and you can see the number of ligands which are bonded with the metal atoms are 6. So the coordination number is 6 for octahedral. And octahedral species are very important. Okay. So all the complexes under octahedral, they are very, very important. Okay. Just a second. Yes. And for the same octahedral geometry, we do have one more hybridization, which is D2sp3. So D2sp3 also has same coordination number 6 and same geometry, octahedral, but hybridization is different. I will show you and I'll tell you the differentiation in the complexes while discussing the complexes. Okay. The very most important are tetrahedral, square planar, and octahedral. sp3, dsp2, sp3d2, and d2sp3. So these are very, very important. So first, we are going to discuss about the octahedral complexes and its related informations. Okay. So octahedral complex is divided into two. One is inner orbital and the other one is outer orbital complex. So first, let me take this inner orbital complex and explain you with an example. So what is inner orbital and why it is called as inner orbital and all, I'll explain. So since the geometry is octahedral or the complex is octahedral, the coordination number is going to be 6. Whether it is inner orbital or outer orbital, it is going to be 6, right? And specifically for inner orbital, the orbitals that is going to get used for hybridization is n-1t, ns, and np. So these three orbitals are now going to take part in the hybridization in case of inner orbital complex. Okay. So if n value is 4, so the p orbital will be 4p, and here it is 4s, and 4 minus 1 is 3, right? So 3d. So if a metal uses its 3d orbital, 4s orbital, and 4p orbital for hybridization, then that particular complex is called as inner orbital complex. So fourth shell is the valence shell, which is the outermost shell, but the inner d orbital is used. The inner shell d orbital is used for the hybridization. That's why it is called as inner orbital complex. Okay. Clear for all? So what is the hybridization of this particular system? Since the metal is using the inner d orbital, the hybridization would be D2sp3. So this is from 3d, this is 4s, and this is 4. D2sp3 will be the hybridization of an inner orbital complex. Okay. So let us take an example and understand this more clearly. So I have taken a cobalt complex for you, which is octahedral in nature. And now, so experiments shows that this particular complex is diamagnetic in nature. Okay. And we can find the oxidation state of cobalt, right? So if cobalt is taken as X, amine is a neutral ligand, NH3 is a neutral ligand, so it will be 0, which will is equal to the charge of the complex, that is +3. So X will be equal to +3. Okay, so the oxidation state of cobalt is +3. Now, I'm going to give you or show you the orbital and the electron occupation of this d orbital. Okay, of cobalt. So what is the general electronic configuration of cobalt? It is 3d7 and 4s2. Now cobalt is present in +3 oxidation state. So what I have to do? I have to remove 3 electrons, right? So I will get 3d6 and 4s0 configuration. So I'll show you the electronic configuration of these two systems. So the first one is for cobalt, which has 3d7 and 4s2. And for cobalt 3+, the orbital would look like this. In 3d, you're having only 6 electrons, whereas in case of 4s, there are no electrons, 0, and 4p also has no electron. Okay. Now, as this complex is diamagnetic, already experiment showed that this complex is diamagnetic. So what is meant by diamagnetism? There will not be paired electron. So if the system contains no unpaired electron, the system contains 0 unpaired electron. Okay, no unpaired electron will be there. Since the complex is diamagnetic, so there should be no unpaired electron in it. So, but here if you can see, there are 4 unpaired electrons present in the metal orbitals. Now what they have to do? They are going to pair among themselves. So all the unpaired electrons, you can see, they are going to get paired. So all the electrons are now going to get paired and the configuration becomes like this. So here in this configuration, you can see there is no unpaired electron present. Okay. Now, how many empty orbitals are there? There are 2 3D empty orbital and 1 4s empty orbital and 3 4p empty orbital. So now the 6 ligands, the 6 NH3 ligands, they will use only the hybridized orbital, right? The hybridized empty orbital. Now, these empty orbitals are now going to intermix among them and they are going to form the D2 sp3 hybridized orbital. D2, 6 empty orbitals are now going to intermix with each other and they are going to give you the D2 sp3 hybridized orbital. Okay. And in this hybridized orbital only, since 6 orbitals are intermixing with each other, you will get 6 hybridized orbital. You will get 6 D2 sp3 hybridized orbital and you can see those 6 D2 sp3 hybridized orbital here as boxes. And now all the 6 ammonia ligands, they are now going to come with their electron pair and form the bond with this empty hybridized orbital of metal. Okay. Now each one is coming with a 2 electron and now they are forming the bond with the metal. Okay. So they have formed the bond now and since there are no d electrons present in the metal system, this system is diamagnetic in nature, and since the ligands are using the inner orbital of the metal, it is called as inner orbital complex, or it is also called as low spin or spin paired complex. It's also called as low spin or spin paired. Mostly if all the electrons are paired, they are called as low spin and spin paired complex. Okay. And what will be the magnetic moment of this complex? Number of unpaired electron is 0. So if you substitute here in this magnetic moment formula, which is n into n plus 2, what you will get? You will substitute 0, right? So the magnetic moment will be 0, which is very, very less. So due to the very low magnetic moment, it is called as low spin or spin paired complex. Okay, clear for all? So this is an example for inner orbital complex where the metal uses its inner shell d orbital for hybridization. All the D2 sp3 will fall under this category. So any doubt any of you have so far from the inner orbital topic? Okay, if you get any doubt in between, you ask me. Okay, I'll go for the next topic, which is outer orbital complex. So for the outer orbital complex also, the coordination number is going to be 6 because it is again an octahedral system. But the orbitals used for hybridization are not n-1d, it is nd. It is nd. It is 4s, it is 4p, and it is 4d. Whereas in the last case, n-1d orbital was used. But here, nd orbital is used. That's why it is called as outer orbital. Okay. So the hybridization that you will get for the system is sp3d2. sp3d2. So let me take an example to make you understand more clearly. So COF6 3- is taken as the example full. Now, this complex is paramagnetic in nature. This complex is paramagnetic in nature, and the oxidation state of cobalt again here is +3 because cobalt is taken as X, and each fluorine will have 1 minus, and we have 6 fluorines, so it is -6, which is equal to the charge on the complex, that is -3, and X will be equal to -3 plus 6. It is +3. Okay. So again, the oxidation state of cobalt is +3, and we are going to have T7 S2 in normal cobalt, and in case of cobalt 3 plus T6 and 4 is 0. D6 and S0. Okay. But they showed that this complex is paramagnetic, right? So means there should be unpaired electrons present in the complex. Okay. Since the complex is paramagnetic in nature, there should be the presence of unpaired electrons in the system. So you cannot pair up these 4 electrons and the 4 unpaired electrons remains as such. Okay. Now, which orbitals are going to intermix? Only the empty orbitals will intermix. So you can see 1 4s, 3 4p and 2 4d. They are now going to intermix with each other and they are forming sp3 and d2 hybridized orbital. Since 6 orbitals are mixing with each other, 6 sp3 d2 hybridized orbital will form, which you can see here as a 6 boxes on the screen. Okay, so these are the 6 sp3d2 hybridized orbital. Now the ligand. Who is the ligand here? F minus is the ligand, right? So this fluoride ion will come up with its electron pair and it will form the bond with the empty sp3d2 hybridized orbital of the metal. Okay, so each one is coming with the 2 electron and they have formed the bond now. Got it? Now the metal is having 3d orbital with 4 unpaired electron. So it is called as outer orbital complex. And since the complex is having unpaired electron, it is high spin. Why it is called as high spin? If the number of unpaired electron is 4, and if you substitute it this formula, what you will get? 4 into 4 plus 2, right? 4 plus 2 is 6 and 6 4 is 24. So we are getting root 24 as the answer. So it is very high, right? So since it has very high magnetic moment, this complex is called as high spin complex or spin free complex. Clear? Any doubts, students? If it is clear to you, just put a thumbs up or type yes in the chat box. So what I have told you. So first one is inner orbital complex. So inner orbital complex uses D2sp3 hybridized orbital, and outer orbital complex system will use sp3 D2 orbital. Inner orbital is used and here outer p orbital is used. Okay. So mostly inner orbital will be diamagnetic in nature and outer orbital complexes will be mostly paramagnetic in nature. So this is the gist of these two. Clear, students? So I'll show you some questions. So take down these 2 questions and solve these questions as an example. Fe F63 minus and CO C2O4. So what is the name of this ligand C2O4? This is oxalate. This is oxalate, which is an anionic ligand with a 2 minus charge. Okay, oxalate ligand, and this is your fluoride ligand. This is monodentate ligand, and this is your bidentate ligand. So do all the calculations and find out whether the given complex is inner orbital or outer orbital. Okay, you have to find out the nature of bonding in both the complexes. Okay, you have to find out whether it is inner orbital complex or outer orbital. And you have to tell me in the next class. Take down this as a homework. Now I'll go with I'll just skip these, the solution of this. Yeah. Now I'll go with the second topic, which is tetrahedral complex. Which is called as tetrahedral system. So in the octahedral, we have discussed 2 complexes. One is inner and the other one is outer. Now under tetrahedral complexes, the coordination number for tetrahedral system is going to be 4. Tetrahedral system is going to have coordination number 4. And what is the hybridization of a tetrahedral, students? What is the hybridization of the central metal atom for tetrahedral system? What is the hybridization of the central metal atom in tetrahedral system? I don't know why you guys are not interacting with me. Huh? So what is the hybridization of the tetrahedral system? Don't maintain this pin drop silence in chemistry class. Okay. So you can interact. The hybridization of tetrahedral is sp3. Hybridization of the tetrahedral is sp3. Okay. And the orbitals used for hybridization for this sp3 system is, the metal is going to use ns and np orbital. Metal is going to use ns and np. So if it is 4s, then the p orbital is 4p. Yeah. So metal uses this type of orbital to give sp3 hybridized system. And I'll take one example for you. I'll take nickel complex. Nickel Cl4 2- complex is taken as an example. And the experiment shows that this complex is paramagnetic in nature and the oxidation state of nickel is going to be +2. How it is going to be +2? Nickel is X and chlorine is -1. And we have 4 chlorine, so -4, which is equal to -2. And X is equal to -2 + 4. So it is going to be +2. Okay. +2 is the hybridization of the nickel. And what is the general electronic configuration of nickel? What is the general electronic configuration of nickel? So the general electronic configuration of nickel is 3d8 and 4s2, right? Now this nickel is in +2 oxidation state. So now the nickel is going to lose 2 of its electron. So what will be the configuration? This 3d8 and 2 electrons from the s orbital has now lost. Now 4 is 0. Okay, this is the configuration of +2 nickel. So you can see the D8 and S2 configuration of neutral nickel and the D8S0 configuration of nickel 2+. Okay, and this complex is paramagnetic in nature. That is what the experiment shows. Means that should be the presence of unpaired electron, right? You should not pair up these 2 electrons. These 2 electrons has to be unpaired in nature. So now, if they are unpaired, the empty orbitals is starting from 4s. So since we have 4 Cl-, the ligand needs 4 hybridized orbital. For that, this 4 atomic orbitals are now going to intermix with each other and they are going to form the 4 sp3 hybridized orbital. And in these 4 sp3 hybridized orbital, 4 Cl-, they are going to come with their electron pairs and form the bond with it. Okay, so they occupied each orbital with 2 electrons. Okay, so this is the hybridized orbital and its occupation. Now, what about this metal? Now, metal is having 2 unpaired electrons, right? Metal is having 2 unpaired electrons in its 3d orbital. You can see. So, since the complex contains 2 unpaired electrons, the type of the complex is high spin. It is high spin or outer orbital complex. Outer orbital complex. And the magnetic moment is very high. Got it? This is how you have to find out the magnetic moment and the number of unpaired electrons and the hybridization of a given species. The first thing is you have to find out the oxidation state of the metal. Okay? And you have to find out the hybridization of the central metal atom. And thirdly, you are going to find out whether the complex is inner orbital or outer orbital based upon the n-1d or nd hybridization. Okay, so that's it, very easy. So now I'll take one more example for you, which is nickel tetracarbonyl complex, and this complex is diamagnetic in nature. Okay, so the oxidation state of nickel is 0 because carbonyl ligand is a neutral ligand. So let me take this nickel as X, and since carbonyl is a neutral ligand, it will be 0. And it is equal to 0. X is equal to 0. So the configuration of nickel 0 is 3d8 and 4s2, right? So all the d8 and s2 electrons are now going to be there for the nickel. Okay. Because s orbitals are always needed for any type of hybridization, this particular two electrons which are there in the 4s orbital, they are now going to get paired with the unpaired electron of 3d orbital. Now you shift these two electrons to them. What happens now? S orbitals become empty and p orbitals are also there with empty state. Now these four orbitals, 4s and 4p, they are going to intermix with each other and they are going to give again sp3 hybridized orbitals. 4 sp3 hybridized orbitals are formed and CO ligand is going to occupy those 4 orbitals to give the corresponding complex. And this is an outer orbital complex but with low magnetic moment. So why there is low magnetic moment? Number of unpaired electron is 0. So obviously mu value will be 0. Mu is nothing but the magnetic moment. So it is very low. Why? Because the oxidation state of nickel is very low. Oxidation state of nickel is very low and that's why it is forming the low magnetic moment complex even though it is outer orbital in nature. Okay? Clear? This is an exception. Since nickel is in a very less oxidation state, this should be the exception for you in tetrahedral complex. Okay. And thirdly, I'll move on to square planar complex. Thirdly, for square planar complex, the coordination number of square planar complex is going to be 4 again. But in square planar system, the metal will use n-1d orbital for hybridization. Okay. In tetrahedral, nd orbital, okay, not nd, only 4s and 4p orbital. But in case of square planar, the metal uses d orbital. Which d orbital? Inner d orbital. So the hybridization would be dsp2. Okay. So we'll discuss this in detail with an example. So I have took nickel tetracyanide complex, and this complex is diamagnetic in nature. Okay. So what is the oxidation state of the nickel in the complex? Can anyone tell me the oxidation state of nickel in the complex? Try for the oxidation state of nickel in the complex. What is the oxidation state of nickel in the complex, students? I'll give you 30 seconds. So try to give me the answer. I want answer from your side. Oxidation state of nickel. Not even a single student has got the answer. It is very easy, right? Huh? So the oxidation state would be yeah, +2. So nickel is taken as X, and for each cyanide, -1 is the charge, and since we have 4 cyanide, it is -4. And the charge in the complex is -2. So what is X? X is equal to -2 + 4, which is equal to +2. Okay, 4 - 2 is 2. Oxidation state of nickel is +2 here. Now, this is the configuration of nickel 0, and here is the configuration of nickel 2+. So the 2 electrons which is there, the s orbital has now lost. Okay, and since the complex is diamagnetic in nature, there should not be any unpaired electron in the system. So now these 2 electrons are going to get paired with each other. Okay, they are now going to get paired with each other, and the empty orbitals are starting from 3d, 4s and 4p. Now what happens? These 4 orbitals are going to intermix to give dsp2 hybridization. dsp2 hybridization. And in these dsp2 hybridized orbitals only, ligands are going to form the or interact with their electrons. So to these 4 dsp2 hybridized orbital, the cyanide ligand, the 4 cyanide ligand is coming with its electron and forming the bond with the hybridized orbital of metal to give the DsP2 hybridization. Okay. So metal is having 0 unpaired electron, no unpaired electron. So it is low spin or inner orbital complex. Why it is called as inner orbital? Metal is using inner d orbital, no? That's why it is called as inner orbital. And it is a low magnetic moment since the number of electron is 0. As the mu value is going to be 0. Clear? Clear for all? So with this, we are going to predict the number of unpaired electrons in square planar platinum cyanide complex. So to find out the number of unpaired electrons present in the given complex, you need to first calculate the oxidation state of the central metal atom. Okay. So platinum belongs to nickel group, nickel, palladium, platinum, right? So the same configuration will be there for platinum also. The one who has joined now from 12th class ID, is that Sandeep? Yes. Good evening, Sandeep. How are you? Where are you for the past 2 weeks? Huh? You are enjoying the Diwali vacation? Okay. Fine, fine. Okay. Okay, okay, okay. Good. Okay, let's continue. Let's continue. What? 0? Oxidation state of platinum is 0? No. Just try once again. I told you that platinum belongs to nickel group. Hitashri is giving +2. Yeah, Hitashri, your answer is correct. And for Sandeep, phone is not available, ma'am. Okay, okay, Sandeep. No issues. No issues. You can go through the lectures later. But anyway, we missed you a lot in the chemistry class. Hope your phone is available for you hereafter. Fine. Hitashri gave the correct answer. It is +2 because the configuration will be D8. If nickel is having 3D8 configuration and 4s2 configuration, palladium would have 4D8. Number of unpaired electron is, yeah. Okay. Jamie Nisamapat, yes. I don't know your name, but you are correct. 48 and 5 is 0. And for platinum, it would be 5D8 and 6 is 0, right? This would be the configuration. Sorry, 2, 6 is 2. And now platinum is taken as X. Cyanide is -4, which is equal to -2, and X is equal to +2. Now for platinum, T8S2 is the configuration. And for platinum 2 plus T8S0 will be the configuration. T8 and S0 will be the configuration. Okay. Yeah. Now what happens? This cyanide always forms diamagnetic complex. So the unpaired electrons will pair up. And unpaired electrons are now going to pair up with each other. So they have paired up. And as you have said, there are 0 unpaired electron present here in the complex. And the hybridization is DsP2. Hybridization is DsP2 for this system. But in the question, we are asked to find out the number of unpaired electrons only. So it is 0. Correct. Correct, students. Good. Now I'll give you one more question for you. Nickel chloride complex is paramagnetic, but nickel carbonyl complex is diamagnetic, even though both are tetrahedral. Why? Can you give me the reason? Nickel tetracarbonyl and nickel tetrachloro, both the complexes I have discussed with you in the class, right? Just before few minutes we have discussed. Can you tell me why one is paramagnetic? Because of unpaired electron. So which is having unpaired electron? Which is having unpaired electron? Nickel chloride complexes are having unpaired electron, right? Yes. The oxidation state for the first complex is +2. Yeah, nickel Cl4 is very good. For nickel 2 plus sp3 hybridization with the 2 unpaired electron, whereas in case of nickel carbonyl, since the electrons are getting paired up, s electrons are going to d orbitals, there are no unpaired electron there. So, 0 unpaired electron. That's why it is diamagnetic in nature. Okay? But you see the hybridization is same for both. Both are having sp3 hybridization and that's why they are tetrahedral in nature. But the number of electrons differs. One is para and the other one is dia. Okay. So this is about the complexes, octahedral, tetrahedral and square planar complexes discussion according to valence bond theory. Now there are some disadvantages in this valence bond theory. Okay. So those disadvantages are the limitations we are going to discuss now. Okay. The first limitation is it involves lot of assumptions. Valence bond theory involves lot of assumptions. Everything is an assumption. So first we took note that only metal hybridized orbital is interacting with the ligand orbital. That itself is an assumption. Okay. Hybridized orbital interacting with the ligand orbital itself is an assumption. So like this, more number of assumptions are involved here and there is no quantitative interpretation of magnetic data of coordination. So magnetic data in the sense, so some are paramagnetic, some are diamagnetic. Experimentally, when they do the calculation, some are found to be paramagnetic in nature. And while doing the theoretical part, they are diamagnetic. So there is no the correct interpretation of this magnetic data for the complex according to valence bond theory. And thirdly, it does not explain the color of the complex. So in all the complexes which we have discussed under this valence bond theory, you might have noticed that we have found out the hybridization, we have got the type of the complex, and we have found out the nature of bonding, and we have got the number of unpaired electrons present, and we have found out the magnetic moment. All these informations were able to find out, but we did not get the color exhibited by the coordination compounds. Coordination compounds are basically colored in nature, but there is no information about the color. So why they are forming the colored compound? Because D block element is present as a central metal atom. D block elements are able to exhibit the color, right? We have discussed this already in the last class. Last lesson. So that information is not given by VBT. And fourthly, it does not give a quantitative interpretation of thermodynamic or kinetic stability of the complex. There is no information about the stability. There is no information about the stability. How long a given compound will be stable. Please repeat about the color, ma'am. Yeah. So you have not attended the D and F block elements classes, right? That's why you're getting doubt over here. Yeah, no problem. I'll explain you. So, all the D block metal ion containing complexes are colored in nature. Okay. All the D block metal ion containing complexes are colored. Means the coordination compound which contains the D block metal ion as the central metal ion should be colored. But from the valence bond theory, we did not arrive at any information related to the color using this particular theory. Okay. So I'll explain you more in detail about the color exhibited by coordination compounds in the next class. Okay. After completing the crystal field theory, I'll explain you the color of the complex. You don't have to worry. Like how coordination compounds are exhibiting the color, that part I will discuss again once I complete the crystal field theory of this lesson. Okay. Clear, Sandeep? Okay, fine. So here, according to VPT, there is no explanation about the color. This you just keep in mind. And the fourth point, as I have told you, there is no explanation about the stability of the complex. How long the complexes are more stable, that type of informations are not given by valence bond theory. And fifth, it does not make any distinction between the strong field ligand and weak field ligand. Okay, so you might have noticed that the CN ligand containing complex, CO containing complex, the CN containing complex, and the CO containing complex were forming the diamagnetic system. But Cl minus containing system, F minus containing system, all these were paramagnetic in nature, right? Means these ligands are called as strong field ligand and these ligands are called as weak field ligand. So valence bond theory did not differentiate the strong field ligand and weak field ligand because in many compounds, you can see. So here the first compound is cyanide complex and this is chlorido complex. Cyanide is forming inner orbital, but chlorido complex is forming outer orbital complex. Why? Why this is forming inner orbital with the diamagnetic nature and why this is forming outer orbital with the paramagnetic nature? What is the reason? What is the nature of the ligand? Why cyanide is a strong field ligand? Why Cl is a weak field ligand? So such kind of differentiation is not given by the valence bond theory. Okay. So these are the limitations of valence bond theory, which is very important. First thing is it involves a lot of assumption, no information about magnetic data, no information about the color, no information about the stability, no information about the strong and weak ligands. Okay. These are the limitations. Let me just summarize the VPT, which we have discussed. So we took three complexes, octahedral, square planar, and tetrahedral. And octahedral, for octahedral, we have studied two hybridization under each, and D2 sp3 formed inner orbital complex and sp3 D2 formed outer orbital complex. And under square planar, the hybridization is dsp2. So metal is using inner d orbital, so it is inner orbital. And tetrahedral hybridization is sp3. And nickel tetrachlorido complex was discussed. And generally, all the D1, D2, D3 electron containing system will always form inner orbital octahedral complex. Okay, just take a note of it or a screenshot of this. D4, 5, 6. They may form inner orbital in some case, and in some cases they will form outer orbital. Okay, and D8 and 9. These two, they always form outer orbital octahedral system. In case of octahedral, these two electron containing species will form only outer orbital complex. And square planar forms inner orbital and tetrahedral also the same thing. In tetrahedral, there is no inner orbital and outer orbital, right? Because it is using only this s orbital and p orbital. No d orbitals are involved in tetrahedral. Sir, there is no such inner outer concept in tetrahedral. Only in case of octahedral we have, and in square planar we have. That's all. Clear? This is the summary of valence bond theory. So what is the time now? It is 4:47. So I'll give you some questions for homework. So take down this question. Among the following ions, which one has the highest magnetic moment value? I think we can solve this question in the class now itself. One question. First question I'll do. I'll do second and third. You have to do and give me the answer. Okay. So let me take the first complex, which is a chromium complex. Yeah, this is a chromium complex. And what is the oxidation state of chromium, students? It is +3, right? Chromium is taken as X. So water is a neutral ligand, so 0, and it is equal to +3. So the oxidation state of chromium is +3. Okay, for normal chromium, what is the configuration? For normal chromium, it is 3d5 and 4 is 1. And for chromium 3 plus, it would be 3d3 and 4 is 0, right? 3 electrons are removed. And this is the configuration of chromium and chromium 3 plus. Chromium 3 plus. Got it? Only 3 electrons are there in the chromium. Now, how many unpaired electrons are there in chromium 3 plus? 3. Answer is 3. Just keep a note of it. Now I'll come to the next complex. Root 6. Yeah, okay. Root 6. Root 6. Root 6 you are getting? No, it is root of n into n plus 2, right? N value is 3. So 3 plus 2 is what? 5. 5 into 3 is 15. Root 15 you will get. Not root 12. It is root 15. 3 plus 2 is 5 and 5 into 3 is again 15, right? N value is 3. So root 15 is the magnetic moment value. Yeah, good. And students, you tell me the number of unpaired electrons present in the second complex, which is there on the screen. What is the oxidation state of iron? Oxidation state of iron is +2, right? Yes, very good. It is +2 because water is a neutral ligand. And what is the configuration of iron? Configuration of normal iron is 3d6 and 4s2. So all of you have to study the 21 to 30 3d series elements with its electronic configuration. Okay. Then only your D and F block elements lesson as well as coordination lesson is going to be very easy for you. Otherwise, it would be different. We are using this electronic configuration in all the topics, right? So you should be very clear about it. Now the oxidation state is 2. So you can find D6S2 in case of normal iron, and it's root 20 you're getting. No, root 20 cannot be the answer. There are 4 unpaired electrons present in iron. Without finding out the root value, just by seeing the number of unpaired electrons itself, you can get the answer. Root 24? Yes. So 4. 4 plus 2 is 6. 6 4s are 24. So you'll get root 24. Okay. So coming to the third complex, what is the oxidation state of zinc? Zinc oxidation state is +2. Yeah. The normal zinc configuration, neutral zinc configuration is 3d10 and 4s2. And for 2 plus, you have to remove 2 electrons from the s orbital. So we will have a 3d10 electron. Yeah, the answer is 0. Answer is going to be 0. Now you can see that which is having the highest magnetic moment value among the 3 given complex. Root 0, root 24 and root 15. The answer is, yeah, iron containing complex. Good. Iron containing complex is having the highest magnetic moment value. Okay, good. It's very easy. You don't have to put the numbers in the formula and get the answer, root value and all. Just by seeing the number of unpaired electron, just by seeing the n value, you can get the answer for this type of question. Clear? So this is enough for today. So in the next class, what we can do? We can start crystal field theory. So we can start with crystal field theory in the next class. Okay. So far, you just go and revise the nomenclature part, isomerism part, Bernoulli's theory, and valence bond theory. Okay. Clear for all? Okay, students, if you have any doubt, you can ask. Otherwise, thank you so much for listening to the class. Bye-bye. Take care. Thank you. Thank you so much for all of you. Bye-bye.